Alright, so this video is going to cover section 8.3 from your text. We're going to be talking about three main topics. First one is graphing linear equations, and the second one will be talking about graphing linear functions, and then the third topic will be about graphing absolute value functions. So let's start off with a basic review or definition of what actually a intercept is. The x-intercept is the point where a graph crosses the x-axis, and of course likewise the y-intercept is the point where a graph crosses the y-axis. So let's just real quick go ahead and put a generic graph here. If I have a line that crosses this graph, this is my y-axis and my x-axis, and I have a line here, that would mean that this would be the y-intercept, and this point right here would be the x-intercept. And what we can always notice about first the y-intercept is that since this point right here, since that point is on the y-axis, the x value there is always 0. So this point is going to look like 0, comma, some y coordinate. And then since the x-intercept is always on the x-axis, this is going to look like a point where the corresponding y value is always 0 because it's on the x-axis. It's not going to be above, so it's not going to have a positive y value. It's not going to be below the y-axis, so it's not going to have a negative y value. The y value is 0, and then the x coordinate can be anything. So we can use that important fact to help us actually find intercepts. To find the x-intercept, go back here and look at this picture, the x-intercept, the y value is always 0. So that's what we do. We let y equal 0, and we solve for x. And for y-intercepts, we let x equal 0, we solve for y. So this is hopefully familiar to you, and the reasoning why. Remember, in math we always want to know why we do things, not just memorize steps. So I could do that for the following equation, and even though this linear equation is kind of an ugly linear equation in two variables, the nice thing about it is if I employ the intercept method to graph, it's really easy, because if I, for example, let x equal 0, the whole first term goes away. So that means that my equation becomes 0 plus 1/3 y equals 2, which means 1/3 y equals 2. And then if I wanted to get the y by itself, I could just multiply both sides by the reciprocal, which in this case is 3/1 or just 3, because then the 3's cancel, and I'm left with y equals 6. So my y-intercept is the point, remember, we let x equal 0, so it's the point 0, comma 6. So let's go ahead and put that point on the graph, the point 0, 6, right here. Okay, and now we're ready to find our x-intercept. Like we said above, we find our x-intercept by letting y equal 0. And when we do that, then that causes our second term to go away. That 1/3 y goes away. And so what we end up with is 2/9 times x plus 0. Again, that's because 1/3 times 0 is 0. That equals 2. So I'm going to rewrite that without the 0. So we have 2/9 x equals 2. And if we're trying to get x by itself, we're trying to solve for x, here's where we want to multiply both sides by the reciprocal again. We want to multiply by 9 over 2, and on this side by 9 over 2. And what we see happen is on the left-hand side, the 9's and the 2's both cross-cancel, or divide out, and then on the right-hand side, the 2's divide out. And so what we're left with is x equals 9. So the x-intercept is the point 9, 0. And we can again put that point on the graph, go over 9 points, make sure we label 9, 0, and then we go ahead and just draw a line through it. And we will have our graph. This is again using the intercept method to graph the equation of the line. Okay, now we reviewed the first day of class about how to graph an equation that looks kind of like what we have posted here. Remember though, we talked about functions being the same things as when we have a function, the f of x is just like the y. So I could kind of think of this as like y equals 2/3 x minus 6. Doesn't really matter which way we have it. The important thing is that we need to know that the slope, you should know this, is 2/3. And we should also know what the y-intercept is, because when we have our y equals mx plus b form, the b is the y-coordinate of our x-intercept, or our y-intercept, excuse me. And remember, for y-intercepts, the x-coordinate is always 0. So x is 0, and then y in this case is going to be -6. And so we could graph something like this. Again, I'm going to go ahead and start off by putting on my axes. And then when we have a linear equation in this form, we can start off with our y-intercept. That's an easy point to put on there. 0, -6. It's going to be down here. 3, 4, 5, 6. And then we can use the slope, which in this case is 2/3. Remember, this is oftentimes thought of as rise over run. To find multiple extra points on the graph, we can rise 2 and run 3. We can go up 2 over 3, which gives us the point 3, -4. And we could do it again. We could keep going. We could go up 2 and over 3 again, which gives us the point 6, -2. And even one more time, we could come up here, up 2 over 3, which gives us the point 9, 0. And then we could go ahead and graph the line that runs through those points. Again, all of this should really be something that we've seen before. It's nothing new. It's review from algebra. But it's something that we need to know moving forward in this class. So that is another example of graphing a linear equation. Or in this case, actually, we call it a linear function because it's got the f of x. Now, what if we have one like this? What is missing in this problem that was in the last problem? Hopefully everybody can see that we're missing the plus b, which means we can think of this, if you want to think about your y equals mx plus b form, you can think of the b as being 0, which in this case means our y-intercept is 0, 0. Which should make sense, because remember we find y-intercepts by letting x equal 0, so really what we have here is we're letting x equal 0. We want to find what f of 0 is, which is 3 times 0, or 0. Our slope is the number in front of the x, which in this case is 3, or we can think of it as 3 over 1 for our rise over run purposes. And so in this case, if I go ahead and work on my graph, I'm going to start at 0, 0, and then I'm going to rise 3 and run 1. Up 3 over 1, which gives us the point 1, 3. Again, we could keep using the slope, but it's not really necessary. 2 points is all we need to graph a line. So there's our line. I have one more example here of a linear function, and this one is different than the previous two, because the previous two had slopes, and this one has no slope. There is no slope on this example. And remember, f of x is kind of like, it means the same thing as y, so this is really saying, let's graph y equals 4, which we should all know is a vertical line or a horizontal line. You decide. The way I like to help students remember this is, if a line has no slope, it's like driving on a road that has no slope. Well, roads that have no slope, are they really steep or are they completely flat? And the answer would be that they are completely flat. They have no slope. And so, in this case, this is just a line that goes through y equals 4. So 1 point, for example, would be the point 0, 4, but I mean 4, 4 is a point. There's a lot of different points that are on this line. We could talk about the point -2, 4. The important thing, though, is that any point on this line, this horizontal line that I'm about to graph, has a y value, or a y coordinate of 4. So that is basically the examples I had for graphing linear functions and linear equations. Now might be a good time to pause your video and go ahead and try self-checks 1 and 2. One thing that I did not talk about yet on any of the 3 examples, so let's go ahead and talk about that before you pause it, is to talk about what is the domain and range when we have a linear function. Well, we can see that this line, it keeps going up, it keeps rising, and it keeps dropping. It doesn't stop going up, it doesn't stop going down, it doesn't stop going right or left. So in this case, the domain is -infinity to infinity, and the range is -infinity to infinity. Covers all the x's and covers all the y's. Now let's go to the second example. Again, this graph, example B, it keeps going up and down, it keeps going right and left. So the domain is -infinity to infinity, and the range is -infinity to infinity. We have a difference with either the domain or the range on the last example. And hopefully everybody can see that it's not the domain that's limited. The domain, it still goes forever to the left and forever to the right. It covers all the x values. What's different is the range, because it doesn't go up and it doesn't go down. It only has one x value. The range in this case is y equals 4. That's it. There's just one value. We could say it's a set. It's just the value 4. Okay, hopefully that makes sense. Now I would go ahead and pause it and try those first 2 self-check problems. Notice this one might be one that's good to use the intercept method. And then the second problem is one you might want to use the using the slope and the y-intercept method. Alright. So let's now go ahead and talk about absolute value functions. What you see before you is a graph of an absolute, or is a table that we can put points. Okay, welcome back. I hope that you didn't have much trouble doing the first two self-check problems. Let's now take a look at how we would graph an absolute value function. And I'm just going to start out with the most basic one, and that's the absolute value of x. And so what I did here is I built a little t-table here, and we're going to go ahead and fill it in. If x is -3, then we would see that the absolute value of -3 is 3. If x is -2, the absolute value of that is 2. If x is -1, the absolute value of that is 1. And the absolute value of 0 is 0. The absolute value of 1 is 1. The absolute value of 2 is 2. And the absolute value of 3 is 3. Which really, these are like our y values. So each of these calculations, for example, when we did -3, that's equal to the absolute value of -3, which is 3. This is how we came up with that value. You can do this sort of calculation for each one of these. It's not really necessary, but what we get is we get a point. We get the point -3 for x and 3 for y. -2, 2. -1, 1. 0, 0. 1, 1. 2, 2. And 3, 3. And these are points that are solutions to the absolute value function f of x equals the absolute value of x. And so I'm going to go ahead and put them on a graph here. And let's see what kind of shape this thing has. And we go ahead and put our points on. We see a shape that looks kind of like a V. Let's go ahead and label our points because we should always label points. -1, 0 over here. And you, as I mentioned earlier, you kind of have this nice V shape. In fact, every absolute value function will have this sort of shape. Now they're not always in the same exact place, but they should always have the sort of V shape. Sometimes they open up, sometimes they open down, sometimes they're shifted right and left or up and down, but they all have this basic shape. Now, anytime we're talking about a function, again, we need to talk about the domain and range. We can see here that for the x's, we have points that go forever in both directions for x. So the domain is -infinity to infinity. It keeps going out to the right and left. However, we are limited for the range. There are no points that go below the x-axis, and so the range is only the positive y value. So this is going to look like 0 to +infinity for the range. Alright, so this example is a bit different than the last one because we have some shifting going on. Let's start out the same way though. Let's take our table of values like we had in the last one, and let's plug in some different x values here. So if we take -3 for example and plug it in, when you plug -3 in for x, -3 plus 3 is 0. 0 minus 4 is -4. Again, all I did there was I was finding f of -3, which is the absolute value of -3 plus 3 minus 4, and that's 0. 0 minus 4 is -4. I'm not going to show the math for all this. Basically, I'm just plugging -2 in for all these. So when I plug -2 in here, I get -2 plus 3 is 1. 1 minus 4 is -3. When I plug -1 in, I get -2. When I plug 0 in, I get -1. When I plug 1 in, I get 0. When I plug 2 in, I get 1. And when I plug 3 in, I get 2. Now, notice the problem here is if I start to put these points on, -3, -4, -2, -3, -1, -2, 0, -1, 1, 0, 2, 1, 3, 2. This is an absolute value function, so we expect, just like in the last example, that we should have some sort of V shape. All we have so far is just a line. So, and it appears as I keep going further and further to the right, this line is just going to go up. Maybe we should see what happens to the left over here. So, you know, this value right here is at, what do we say, -3, -4. So maybe I should try plugging in a value to the left of that value, like x equals -4. -4 is the next value to the left over here. If I plug in -4, I get -4 plus 3. -4 plus 3 is -1. Absolute value -1 is +1. 1 minus 3 is -3. So we have -4, -3. Now we're starting to go in the right direction here. Starting to see that V shape happen. So maybe one more value, -5. If I plug -5 in, -5 plus 3 is -2. The absolute value of -2 is +2, and 2 minus 4 is -2. So we have -5, -2. Put some of these points in over here. This was 1, -2. This was 1, 0. This was 3, 2. You get the idea. This graph should look something like this. Okay, and again we see that V shape. It's in a different spot. This graph is different than in a different spot than the last one. Again though, we can talk about the domain and range just like the last one. It turns out pretty much actually every absolute value function has the same domain, because you can plug in any x value in here. It doesn't matter what it is. Notice that this graph keeps going out here to the right, keeps going out to the right, and it keeps going out to the left as it goes up. So domain is again everything. It's -infinity to +infinity. But when I'm talking about the y's, the range here, it's not everything. Yes, the graph does continue to go up to +infinity, but it stops down here. Where does it stop? It stops at -4. So the range is everything from -4 to infinity. Now I already mentioned this graph in comparison to the last one is different. It's the same shape, it's the V shape, but this one, if you will, it It starts here at 0, 0. In fact, we call that point right there, it has a special name. It's called the vertex. Well, in this graph, the vertex is at 0, 0. In this graph, the vertex is at -3, -4. Now, look at what's going on here. It looks like that if I take and look at the opposite of this +3 that's added to the x, so it's x plus 3, well, it turns out that this means that there is a shift left by 3. You always have to kind of think about it in the opposite. So if that's +3, normally think a positive is going to the right. Well, it turns out that positive, we're going to go to the left here. And then the part that's outside the absolute value, this -4, that gives us a shift down by 4. And so what we can do is take that last graph. Let me just kind of sketch it real quick here in green. Remember, it looked like this. It was still the V shape, but it had the vertex at 0, 0. Basically, we just take that whole graph and we shift it left 3 and down 4, and we get this new graph. Let's take a look at one more of these. Similar idea, just one thing that's slightly different. Just like the last one, remember, whatever is going on with the x, we think the opposite. So since this is x minus 1, we're going to be doing a shift right by 1. And then the part that's outside the absolute value, that's the up or down shift. So this is a shift up by 5. Now the other thing that's different is then that last example, the absolute value is just a positive absolute value here, and here in the second example, I guess it's the third example, this is a negative in front. Well, what that does is it makes the graph open down. It flips it upside down. Whenever you see the negative out front there, it's going to flip the graph upside down. So let's use this idea of shifting this time. Rather than going out and trying to find points right away, let's start the graph at 0, 0, and let's shift right 1 and up by 5. That takes us to that point right there. That's the point 1, 5. What I'm saying is I expect this graph that for this right here, this point to be the vertex, and I expect the graph to open down, to come down like this. And we can verify this by doing a few points here. If we choose x, and then we find the negative absolute value of x minus 1 plus 5. So this is when x equals 1. The next value to the left here is 0. If I plug 0 in, 0 minus 1 is -1. The absolute value of that is +1, but then there's a negative out front, which makes it -1 again. If we add -1 to 5, we get 4. Next point to the right, if I go to the right one, that would be 2. If I plug 2 in here, 2 minus 1 is 1, but there's a negative out in front, which makes that again -1. -1 plus 5 is 4 again. So we just found, here's the point 0, 4, and we have the point 2, 4. Okay. Another thing that we haven't mentioned yet that I want to mention now is that when we have absolute value functions, we have this kind of symmetry going on, that about this vertex, notice, go back to the last example. Here's my vertex here. These points over here are mirror images of each other across this kind of vertical imaginary line that goes up through the vertex. So if there's a point up 1 over 1, then there's another point up 1 over 1 over here. If there's a point, this point right here, 1, -2, that's up 2 over 2. Then there's got to be another point on the left side up 2 over 2. And so it turns out this graph is going to, There's going to be another point here. This graph is going to come down like this. We again want to talk about the domain and range of these two. Domain for the first is again negative infinity to infinity. The range now is a little different. We're not going up to infinity this time. The graph is opening down, so it's going down to, you guessed it, negative infinity. So this is going to be negative infinity, because we always go from smallest to biggest. Negative infinity, and where does it stop? It stops at 5 with the bracket. And then the last example here, we want to go the opposite way. If we're given a graph, we should be able to find the function. So we know that the basic absolute value function starts at 0, 0. This one obviously does not have a vertex at 0, 0. It's been shifted where? You should say it's been shifted left 6. So remember the shifting right left is controlled by the part that's inside the absolute value. So if we're shifting left by 6, we think the opposite. So we want to have an absolute value of x, not minus 6, but x plus 6. Does it shift up or down at all from 0? Nope, the vertex is right on 0. So there's not going to be anything out here after the absolute value. It's just going to be f of x equals the absolute value of x plus 6. Alright, thanks for your time. We'll see you in class.